అప్లోడ్ అయింది. కాలే రెండు సార్లు మంచిగా అయింది. ఇప్పుడు అదేనా
ఇక్కడ ఆన్ అయింది కదరా, మళ్ళీ స్టాప్ చేసి స్టార్ట్ చేయనా? ఇదంతా వస్తుంది ఇప్పుడు డిస్కషన్ అంతా.
Students, hello, good morning students. Hello, good morning.
Good morning, madam.
Good morning. Today we are going to discuss about the graphics concept. So yesterday we are see some of the questions on trees concept. Now we are going to discuss about some graphs. Okay. After completion of these graphs, next we can discuss about some questions regarding trees and graphs. Okay. Now graph is also one of the non-linear data structure. Means non-linear in the sense the data is stored in non-contiguous memory locations. Means non-contiguous memory locations, and at the same time that means not in a sequential memory locations. Okay, here graphs are collection of nodes. These collection like that, tree is also nothing but graph, but there is no cycles in the tree. Okay, coming to the graphs are a collection of nodes connected by edges, and these that is, it contains some number of nodes and edges. That is, this is a notation for graph equal to v comma e. Here v comma e, where v is a set of nodes and e is a set of edges. Okay. Now these graphs are useful in a number of applications. We know that whenever we can find the shortest path between the source and destination. So between the source and destination, there exists a number of paths. Find out which one is the shortest one. So for that, graphs concept is very much useful, and at the same time network applications also. There is maximum flow problem. That means how much speedily the data can transfer from one location to other location. For that, which path is useful. Okay. Here these graphs are like these also, that means graphs are the connected components. That is, graphs unlike trees are more general, but they can have connected components. Whereas coming to the trees and graphs, both are connected components. The difference between the trees and graphs is, so tree is a graph and there is a acyclic graph. There is no cycles. And here two types of graphs are there. One is a directed graph and other one is an undirected graph. So in the directed graph, there is no direction. You can observe here, this first one is a this is the first figure. Here there is no directions. That means from node 1 to, we can move to node 2. From 2 to 1 is also, there is both directions path is exist. From here to here and here to here path is exist. So that's why, so this is called as a undirected graph, and this is what the directed graph. That means here in this case, from 1 to 2 that is path is exist, as well as 2 to 1 path is also exist. So coming to here 2 to 5, so you can observe here 2 to 3, there is no path. There is a path from 2 to 3 as well as 3 to 2. Suppose you can observe here 2 to 3, here the path is exist from only 3 to 2, not both sides. So that is the difference between the direction path and undirected graph and directed graph. Suppose here in this graph, how many number of edges are exist? That means, and 2 to 3, 3 to 5, and 5 4, next 4 2, next 1 3. That means, so it contains number of vertices v equal to 1 2 3 4 5, and coming to the edges 1 2 1 3 2 3 2 4 3 5 and 4 5. So whenever we are given these two vertices like this in this type of braces, this is a flower braces. Now this is nothing but the edge between two nodes, but there is no direction. Suppose that edge is represent like this within the parenthesis. This is the left parenthesis and right parenthesis. Then we can say that here direction is exist. In this case, there is no direction. That means undirected path is in the undirected path, the edge is denoted by in the flower braces, whereas directed graph, the edge is denoted in parentheses only. Okay. Now here, before discussing the graph representation, first we can discuss about the graph terminology. So a graph is an ordered pair. That means ordered pair means it contains number of pairs. This is one pair and this is one pair. Like that, it contains number of ordered pairs. There is collection of ordered pairs with a set of vertices or nodes. Okay, and edges. The edges are used to connect these nodes. Okay, V is a set of vertices or nodes and E is a set of edges. Okay, coming to subgraph, a subgraph of a graph as a subset of the vertices and edges. For example, suppose you can take the graph is only 1 2 3. Now this is the graph G, and other graph is G dash. Now 1 2 and 3. So now this graph is called a subgraph to this graph G. Okay, the edges indicates how we can move through the graph. That means the purpose of these edges are how the path is exist among these vertices. From here to here some path is exist. From here to here path is exist. Coming to here path is exist. Now here the path is exist. Like that, how the path is exist, how we can move from one node to other node. So that is represented through this edge. Now coming to the path is a subset of E. That means path is nothing but what is the path between 1 to otherwise 1 4. What is the path exists between 1 4. So here from 1 to 2 path is there, 2 to 1 path is there, 1 3 path is there, and 1 2 path is there. Suppose you can observe here there is no path to this 4 from this 1. Suppose you can observe the path from 1 to 5. That means here 1 to 3 path is edges exist, and 3 to 2 edges exist. There is no edge from 2 to 5. So that there is no path exist from 1 to 5 also. So coming to this undirected graph, here you can observe 1 to 4 there is a path is exists. That means 1 to 2 path is there. Otherwise 2 to 4 path is there. 1 to 2, 2 to 4, or 1 to 2 to 3, and 3 to 5, 5 to 4. That means in the undirected graph from one vertex to another vertex exists path. But in the directed graph, if direction is exist only, we can move from one node to another node. So that a path is a subset of edges. That means here suppose from your path from 1 to 2, it contains subset of edges. 1 2 is a edge. This number of edges. Suppose you can observe find out any path between the two nodes. That means that path contains of edges. That edges are subset of these edges. Now a graph is connected if there is at least one path between every pair of nodes. When we say that the graph is connected graph, that means suppose you can take these two pair of edges. Now this is a connected graph. So suppose from here to here some path is exist. Now that is a graph is connected if there is at least one path between every pair of nodes. Every pair of nodes మధ్యలో మనకి path exist అయింది అనుకోండి, then we can say that there is a connected graph. So in the coming to the 2 to 1 path is exist, 2 to 3 path is exist. Okay, 2 to 4 is also exist, and 2 to 5 is also exist. Coming to the 3 to 1 path is exist, and 3 to 2 path is exist. Next 3 to 4. So how the 3 to 4? That means 3 to 2 and 2 to 4. Otherwise 3 to 1, 1 to 2, and 3 to 4. And coming to 3 to 5 path is exist. Now this is a connected graph. Suppose you can observe here the undirected graph, directed graph. Here 1 to 2 there is no path, 1 to 2 there is no path, and 1 to 2 there is no path. Next here 1 to 2 path is exist, and 2 to 1 is also path is exist. Coming to 1 3 path is exist. Now coming to this 1 to 4, here there is no path from 1 to 4. Now we can say that this is not a connected graph. Why? Because there is every pair of vertices there exists a path, then we can say that the graph is connected. Otherwise that is not a connected graph. Here you can observe from 1 to 2 path is there, and 2 to 5 there is no path, from 2 to 4. So that this is not a connected graph. That is, a graph is connected if there is at least one path between every pair of nodes. The next one is length. What is the length of the path in a graph? That is, the length of a path in a graph is the number of edges in a path. Suppose here from 1 to 5 maximum length, that is length of a graph is nothing but maximum length. That means the length of a path in a graph is number of edges in a path. Okay, here from 1 to 4, okay, 1 to 2, 2 to 3, 3 to 5, 5 to 4. That means the path is for this is 4. Complete graph is nothing but, so this complete graph is a graph in that edge between every pair of nodes. That means in the trees concept we have discussed this one, regular graph. Regular graph nothing but, so every node have same number of children. That means every non-leaf node has same number of children. This is called as a regular tree. Now coming to the complete graph, suppose you can take one node. Suppose if our graph contains 5 nodes, suppose you can take one node. from that one node remaining 4 nodes have some path. Okay, then other one, for example, suppose here 1 to 2 path is there, 1 to 3 path is there, 1 to 4 is there. Now 1 to 5, then 2 to 1, 2 to 4, 2 to 3, then 2 to 5, okay, 2 to 4 and 2 to 5, then this is a complete graph. Now 3 to 2, 3 to 1, 3 to 5, again 3 to 4. Now this is called as what? Complete graph. So coming to this 5, 5 to 4 is there, 5 to 1, 5 to 2, 5 to 3. Remain, that means you can take one edge, one node, and edge can form it with remaining all the nodes, then that graph is called as complete graph. A weight graph nothing but, so on the edge we can assign some weight. Suppose this is the source and this is the destination. What is the distance between these two? So that is represented by using some weight that is on the edge. Now a cycle is a path that begin and end at the same node. Here you can observe here 1 to 2, 1 to 3, 3 to 5, 5 to 4 and 4 to 2, 2 to 1. End points are same. That means initial point and last point. If initial and last points are same, then the path is exist. That means a cycle is a path that begins and ends at the same node, then that is called as a cycle. So as acyclic graph nothing but there is no cycle. Suppose you can take the tree, that is a acyclic graph. Suppose you can observe here there is no path between these two, 4 and 5. So this is what the acyclic graph. Now coming to this, an acyclic connected graph is also called an unrooted tree. An acyclic connected graph is also called an unrooted tree. That is nothing but tree is a acyclic graph. An acyclic connected graph is also called as unrooted tree. That means sometimes, suppose here like this, here an acyclic connected graph is also called an unrooted tree. Means suppose here this is the acyclic graph. Suppose you can remove this edge 4 to 5. Now this is the acyclic graph but not a tree. Why? Because so, and one more is okay. So this is what the acyclic graph. Okay, but not number of roots. Suppose remove this 1 to 2 and remove this 5 to 3. Now this is the acyclic graph, but there is no node as designated as root. Next, number of edges and number of edges in undirected graph. How many number of edges are there in undirected graph and directed graph? So this is also one of the important concept. Okay, here number of edges in undirected graph, the number of possible pairs in an n vertex, that n vertex of a graph is n into n minus 1. Suppose if a graph contains 3 vertices, okay, 3 vertices, how many number of possible pairs are there? Okay, that means 3 into 3 minus 1 means 2. Okay, that means A to B edge is possible, and next A2, that means the number of possible pairs in n vertex is n into n minus 1. And coming to, since that means UV is the same edge as VU, it means because there is no direction from U to V. So in that case, U to V is same edge as V to U. That's why the number of edges in undirected graph is n into n minus 1 by 2. Suppose for example, A to B is there and A to B one edge is there as well as B to A one edge is there. Then next here A to B one edge and B to B to C one edge and A to C. Okay. So here AB or BA both are same. So that's why we can treat it as only one edge. So that how many number of edges are there? A to B, A to C and B to C. So that total maximum edges in undirected graph, if that graph contains 3 nodes, that is 3 into 2 minus 1 divided by 2. That means only 3 edges are exist. Suppose for example in the previous graph, so this is the undirected graph. So this is the undirected graph. In this undirected graph, how many number of edges are exist? From 1 to 2, there is one edge. 1 to 3 one edge, 1 to 4 one edge and 1 to 5 one edge. That means 4 edges. Every node have exist 4 edges. So this node have 4 edges. So this node 4 edges, this node 4 edges, this node 4 edges. That means 5 into n minus 1 means 4 minus 1. 5 into 4 5 into 5 minus 1. That is totally 20 pairs are exist. In that 1 comma 2 is same as 2 comma 1. Both are same. That's why we are dividing that divided by 2. So that's why how many number of edges are exist? That is total 10 edges are exist. That means 1 to 2 one edge, 1 to 3 one edge, 1 to 5 one edge, 1 to 4 one edge. That means 4 to 1 is same, 5 to 1 is same, 5 to 2 is same, 3 to 1 is same. So that it is divided by 2. That means n into n minus 1 divided by 2. So that maximum edges are exist in the undirected graph n into n minus 1 divided by 2. Okay, n into n minus 1. That means the possible number of pairs are n into n minus 1. But coming to the total number of edges are n into n minus 1 divided by 2. Okay. Suppose are you here? The whiteboard is not presenting, so just I am share the screen only. Okay, whiteboard is not appears here. Now, so coming to the number of edges in directed graph, how many number of edges are there? That means A to B is different from B to A. So that number of possibilities are twice. That is n into n minus 1. The number of possible pairs in n vertex of a graph is n into n minus 1. That means here u comma v is not same edge as v comma u. That means A to B there is edges exist. So suppose you can observe here 1 to A, 1 to 3 edge is there. From 3 to 1 there is no edge. So that 1 to 1 3 is different from 3 to 1. So that's why possible pairs are n into n minus 1, and coming to the maximum number of edges are n into n minus 1. Thus the number of edges in a directed graph is n into n minus 1, that is less than or equal to n into n minus 1. So how many number of nodes are there? Suppose here 3 nodes are there, so that maximum number of edges are 3 into 3 minus 1, that means 6 minus 6 only. That means a to b 1 edge, b to a, as well as a to c and c to a, and coming to b to c, c to b. Total 6 edges are exist. Okay, that is less than or equal to, that possible number of edges in a directed graph is less than or equal to n into n minus 1. And whereas coming to the linear data structures as well as trees concept, so these are represented in different ways. That means we know that two representations, one is a sequential representation and other one is a pointer representation or linked list representation. So coming to the sequential representation, nothing but, that means here by using, that means we know that two representation, one is the array representation and pointer representation, or static representation or dynamic representation. So coming to the here in graphs, here two representations are there. For graphs to be computationally useful, so they can be represented conveniently in our programs. So for that here two representations are there. Those two representations, one is the adjacency matrix and adjacency list. So coming to the adjacency matrix, this is the array representation, that is sequential representation. Okay, why? Because we are called here sequential representation, means to store any vertex, there sequential, that means sequential locations are there, so that arrays concept. And coming to the linked list representation, here adjacency list is used. So now see first what is the adjacency matrix. So adjacency matrix, nothing but this is a square matrix, so it contains n into n. Square matrix, nothing but same rows and same columns, you know that, that is same square matrix with Boolean values, means so that matrix contains only zeros and ones. Okay, square matrix or square grid of Boolean values, that means that that is a matrix only, that matrix contains only zeros and ones. So if the graph contains n number of vertices, then matrix contain n number of vertices and n number of rows and n number of columns. So the intersection of row and column must be 0 or 1. Either 0 or 1. That's why adjacency matrix is a square grid that contains only Boolean values. So how we can place 1 and 0? For that, so for two vertices, here I and j are the two vertices. So if there is an edge exists between I and j, okay, then you can place 1, otherwise 0. That means here for two vertices numbered I and j, okay, two vertices means so first vertex number is I, second vertex number j. The elemented row I and column j is wrong ichchamandi, is true nothing but 1. Here true nothing but 1. If there is an edge from 1 to j, I to j, so there exists any edge between vertices I and j, then the intersection of row and column contains 1. So here true nothing but 1, otherwise false, 0. Okay, type mistake. Now see here, so this is the adjacency matrix for this undirected graph. Suppose here you can observe how many number of vertices are there? 5 vertices. Okay, these are the 5 vertices, so that this matrix contains 5 columns and 5 rows. That means these are the 5 rows and 5 columns. So this is row values are I. Okay, I contains values 1 to 5 because 5 vertices are there, and coming to the columns, 5 vertices, 5 because of 5 vertices, number of columns also 5. So the intersection, that means if this is the ith column and jth row, that means first column, first row and first column. So in the first column and first row, if there is any edges exist, suppose if it exists path from 1 to 1 means self loop, or simply say that loop. self loop in the sense edge exists with the same vertex, then that is called as a self loop. Okay, loop in the sense what, here, from here, here, and this, like this is a self loop. So if the loop is exist like this, then here one, so there is no loops, so that this, there is no edges exist, this is 0. And coming to here, 1 to 2 path is exist, 1 to 3 path is exist, and 1 to 4 path is exist. That's why here the intersection, that means this is the 8th row and 2nd column, so that here edges exist, so then the value is 1. Okay, here from 1 to 2, 1 to 2, 1 to 3 path is exist, now 1, 1 to 4 path is exist, 1, and 1 to 5 there is no path. From 1 to 5 there is no path, direct path, so that this is a 0. So in the sense, simply say that there is no edge exist. Path is exist, but there is no edge. And coming to here, 2 to 1. So this is the undirected graph. There is a edge between 1 to 2 and 2 to 1. Both edges are same. That's why 2 to 1 edge is there. 2 to 3 there is 2 to 2 there is no edge. 2 to 3 there is no edge. 2 to 4 edge is there. Okay. Now coming to here, 3 to 1. So here 3 to 1, 3 to 4, 3 to 5. 3 to 2 there is no edge. 3 to 3 also there is no edge. So coming to the 4, 4 to 1 edge is there, 4 to 2 edge is there, 4 to 3 edge is there, 4 to 5 edge is there, 4 to 4 there is no edge. Coming to the 5, here only 2 edges are there, that's why in this row only 2 ones are there. So that's why you can count how many number of ones are there here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Suppose you can observe here how many number of edges are there. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That means divided by 2. N into n minus 1 divided by 2. How many number of vertices here? Maximum n untai manaki less than or equal to n into n minus 1 divided by 2. Okay. So maximum n into n minus 1 divided by 2. So that means how many number of edges are exist? Less than or equal to n into n minus 1 divided by 2. So that's why here 7 edges are there, here 7 ones are there. So because of this is undirected graph, that means 14 divided by 2 means 7 edges are exist here. Suppose coming to the directed graph, so this is the directed graph. In this case, how matrix is represented? Instead of 1 and zeros, here how many number of edges are exist? Okay. So observe here from 1 to 2, 1 to 1 there is no edge. Coming to this 1 to 2, here 3 edges are there. Okay, that's why this is the 3. 1 to 3 there is no edge. So from 1 to 3 there is no edge, that's why this is 0. And coming to 1 to 4 only one edge is exist, that's why this is 1. And coming to this 2, so there is here 2 to 1 there is no edge. From 2 to 1 there is no edge. Now observe here how many self loop is exist. This is self loop. And coming to here 2 to 3, 2 edges are there. That's why this is a 2. And here what 3. 3 to 2 to 4 there is no edge. And coming to 4 to 1 there is no edge. 4 to 2, 3 to 1 there is no edge. Okay, 3 to 2 one edge is there. 3 to 3 2 edges are there. 3 to 4 there is no edge. And from 4 there is no edges start from this 4, that's why all are zeros. So here how many number of edges are exist? 1, 2, 3, 4, 5, 6, 3, 3, 6, 7, 8, 9, 10. Total 10. Okay, now add all this 3, 4, 5, 6, 7, 8, 9, 10. So total edges 10. Here also 10 are there. So maximum, that means here maximum means what, and ikkada manaki 1, 2, 3, 4. It is 4 into 4 minus 1, that means 12. But here 12 are the different pipes. 12 edges are different edges. Suppose you can observe here 1 to 2, 3 times is there. So just we can take only one time. That means how many number of different unique edges are possible in the directed graph, that is n into n minus 1. Okay. So this is what the adjacency matrix for directed graph. So coming to the adjacency list,
In a adjacency list, here it contains n rows of the adjacency list are represented as n linked list. That means, suppose if our graph contain n number of nodes, in that case n number of linked lists are there. Okay. For example, suppose this is the graph. Suppose this is one graph. Here how many number of edges are there? Here 5 edges are there. So that 5 linked lists are exist. Okay. That is, in a adjacency list, the n rows of the adjacency list are represented as n linked list. So n rows nothing but, suppose 5 nodes are there, 5 rows of adjacency list are represented. Each and every one is represented with one linked list. One list for each vertex. Okay. Nothing but, suppose here from 1 to 2 and 2 to 4 and 4 to 5. This is one representation. Coming to this 1 to 4 and 4 to 5. So like that some representations are there. A graph of n nodes is represented by one dimensional array. A graph of n nodes is represented by how many number of nodes are there in the graph, that is represented by one dimensional array. Okay, where L of I is the linked list containing all the nodes adjacency from the node I. Okay, here L of I, L of 1, L of 2, L of 3, L of 4, L of 5. అలా మనకి 5 nodes తో array ఉంటుంది. So each and every array is nothing but linked list containing all the nodes adjacent from that node. Means here our array contains the 5 nodes. This is the L of 1. So this L of 1 is a linked list. It contains all the nodes adjacent to that 1. Okay. So here adjacent means what? Here coming to adjacency in the sense, here 1 and 2 are the adjacent elements. Why? Because there is an edge exists between these two. 1 is, that means 2 is the adjacent element to this one, and 4 is also adjacent to this, and 3 is also adjacent to this. Okay. Now L of I is a linked list. It contains all the elements, those are adjacent to this node 1. Now here, that is the nodes in the list I are in particular, no particular order. That means here 1 to edge is there, 1 to 4 edge is there, 1 to 3 edge is there. That means 2, 4, 3 order is different. That means compulsory to that order must be 2, 4, 3. This is not. So the order is different. Either 2, 3, 4 or 3, 2, 4 or 3, 4, 2. So whatever the order, whatever the combinations, it is there. Okay. For a weighted graph, so this list would also include the weight for each edge. Okay. So that means in the end, along with the adjacency vertex, in the weighted graph, it also contains weight of that particular edge. So now this is the example for the undirected graph, adjacency list for undirected graph. So in this graph, this many number of edges. That means here how many number of edges are there? 1, 2, 3, 1, 2, 3, 4, 5, 6 edges. 1, 2, 3, 4, 5, 6 edges are there. Okay. So maximum how many number of edges are exist here? Total 5 vertices. So that 5 into 4 divided by 2. Maximum 10 edges are exist. So how many number of maximum pairs exist here? N into n minus 1. Okay. In this undirected graph, so this is some array. This array contains all the vertices, first, second, third, fourth, fifth. Okay. Now from the first, how many number of adjacency vertices are there? One is the 2 and second one is 3. Okay. So in this here, first here it contains address of this node. Now this contains value as well as address of this node, and last one is a null. And next this contains the address of first one, that means second. This is a second node, and it adjacent to this one, adjacent to this 3, adjacent to this 4, means 1, 3, 4. And coming to this third, so which vertices are adjacent to this 3? That means adjacent vertices are 2, 1, 5. 1 to 5. 1 to 5. So whatever the order. So first you should take the 5, after that 1, after that 2. There is no problem. That means there is no specific order. Okay, here it contains linked list concept. That means first it stores the address of this one, next others node's address, next other node's address. So like that 4, whatever the elements, then which elements are adjacent to this 4. That one is a 2 and other one is a 5. I am coming to the 5, so one is a 3 and other one is 4. So this is the adjacency list for undirected graph. So coming to the directed graph, so this is the adjacency list for directed graph. So first of all, it also contains some array. That array contains n number of vertices. This array contains n number of vertices. In this n number of vertices, so which first vertex adjacent to which vertices? That is, suppose here this contains the address of here 1. So this represents first 1. This 1 adjacent to 2 as well as 3. Here 2, 3. Now coming to 2, 2 is only adjacent to 1 because this is a directed graph. From 2 to 1 only direction is exists. That's why 1 is the adjacent element or adjacent node to this node. And coming to the 3, so here from 3 to 2 only one node is exist, one adjacent is exist. So that's why this is for the 2. And coming to the 4, 3 and 5. From 5, 2 and 4. So this is the adjacency list for directed graph. So before discussing this, and one more concept, there is an in degrees and out degree concept. That means already we have discussed this in degree and out degree concept in trees. Here, suppose you can observe here, what is the in degree and out degree for this one? In degree means how many number of edges are incident into this vertex, that is called as in degree. Okay, and coming to the out degree, how many number of edges instant from that vertex. Instant from that vertex. That means suppose for example you can take this is the node. From this node, how many number of edges are instant from this node? That means one edge is to 3 and other edge is to 2. That's why out degree is 2 and in degree is only 1. So 2 comma 1. Otherwise in degree and out degree. So in degree 1 and out degree 2. Okay. Then next in degree for this one is 3 and out degree is 1. So that is 3 comma 1. So coming to the in degree for this 2 comma 1. So in degree for this that means in degree and out degree for this, in degree 1 and out degree 2. Here in degree 1 and out degree 2. That means here 1 comma 2, here 3 comma 2, 1 comma 2, 1 comma 2 and 1 comma 2. So this is called as a degree sequence. Degree sequence means each and every vertex in degree and out degree is nothing but degree sequence. So what about this undirected graph? So for this undirected graph, in degrees and out degrees both are same. Why? Because there is an edge exists from 1 to 2 as well as 2 to 1. So that's why in degree and out degrees are same. So in that case, just we are saying the degree of the vertex. So coming to the undirected graph, there is no concept of in degree as and out degree, because in degrees and out degrees both are same. That's why we are take here degree of the vertex. That means degree of this vertex is 2. How many edges are instant from or instant to, and how many vertices. That means degree sequence of this degree for this 2 and for this 3, for this also 3, for this 2 and for this 2. That means what is the degree sequence of this undirected graph is 2, 3, 3, 2, 2. There is a degree sequence for this. Here 2, here 3, here 3, here 2, here 2. Okay, that is the degree sequence of this graph is 2, 3, 3, 2, 2. In this case, the degree sequence is what? Here the degree sequence is 1 comma 2, 3 comma 1, 1 comma 2, 1 comma 2 and 1 comma 2. So this is the degree sequence for this directed graph. So in the same way, here in the but that means in tree also we have discussed about the traversals mechanism. Traversals, that means traversal in the sense, so starts from one vertex, visit all the vertices. So in the tree, two different types of traversals are there, whereas in graphs, in the trees, three different traversal mechanisms are there. We know that those are pre-order traversal, in-order traversal, and post-order traversal. And coming to the graph traversals, so here, what is the use of these graph traversals? That means you can start from one vertex and visit remaining all the vertices to move some particular destination. So that traversals are required. Here two different types of traversals are there. One is a depth first traversal, other one is a breadth first traversal, or simply say the depth first search algorithm and breadth first search algorithm. So here some algorithms required, that means whenever we can find out some shortest distance, in that case we are using the different algorithms. So this cross algorithms, Prim's algorithms, Kruskals algorithms, these are the different algorithms. So in these different algorithms we are using some traversal mechanisms. Okay, some algorithms requires that every vertex, some algorithms requires that every vertex of a graph be visited exactly once. Okay, exactly, graph can visited exactly once. Okay, so in that case the order in which vertices are visited may be important. That means order of the vertices are visited may be important. Why? Because when economy start చేస్తున్నాం ఎక్కడ end అవుతున్నాం. So that is the most important concept, that is the order in which the vertices are visited may be important and may depend upon their particular algorithms. So that here two different algorithms or two different traversals are there. One is a depth first and breadth first. So first we can discuss the depth first search algorithm. In the DFS, so this DFS, it starts at the vertex V of the G as a start vertex and V is a marked as visited. So then each unvisited vertex adjacent to V is searched using the DFS recursively. That means all the adjacent vertices, first you can find out all the adjacent vertices. Once all the adjacent vertices that can be reached from V have been visited, the search is completed. Suppose if some vertices remains unvisited, now we can select that unvisited vertex as a new start vertex and then repeat the process until all the vertices of G are marked visited. Now see for this example, here first, here in the depth first search example, so first you can take one vertex, either any vertex, not only one, so 7 also, 6 also, 5 also, 4 also, 9, any vertex you can take as a starting vertex. Okay, here I am take the starting vertex as 1. So first you can take this one and now you can make it as a visited. After that you can take what are the edges adjacent to this. So adjacent to this. So for this adjacent are 2 and 8. Okay, 2 and 8. In that case, so first you can take only one edge, 2 or either 8, whatever it may be, but you can choose only one vertex. So that now 2 is a adjacent one. That means each unvisited vertex adjacent to V is searched using DFS recursively. Okay, that means first depth first search. That means first depth wise. Okay, so depth wise nothing but first here depth is 0. Now after that 2 and after that 8. From these both of these two, first you can choose only 2. Okay, from 2 then next choose from 2, 3 and 8 both are there. Okay, from these two you can take 3 next step. So from the 3, here 3 to 4 is there, 3 to 8 is there. Okay, that means from 1 to 2 Okay, and here adjacent are 2 and 8. Okay, now you can take these two, okay, these two, and place these elements. That means first of all, unvisited vertex, starting vertex is stored into the stack. Okay, this starting vertex is stored into this stack. Okay, after that, now here two edges are there, these two edges are, two nodes are there, these two nodes are adjacent to this one, so that first you can place these two. Okay, okay, so first you can choose this one. After that, adjacent vertex 2 and 8. From these two, first you can visit these two. After that, what are the elements are adjacent to this one? So 3 and 8. Okay, so now suppose you can take this 1 to 8 already is there, so that 1 is visited and 2 is visited. The next depth, that is the 3. Okay, after that, from 3 to 4 is there and 3 to 8 is there. First 3 to 4, then next 3 to 8. Okay, so after, that is 1, 2, 3, next 4, from 4, 7. Okay, then next here, next 7 to 5, next 6, and next 8. Okay, after that 9. So ఇక్కడ ఎలా తీసుకున్నాం, first 1, next depth 2 and 8. So from this first you can take 2, from this 2 to, and first of all we are storing all the elements 1 2 3 4 up to 9 are stored into some array. So first you can choose 1. So from 1 to 8 is there. So from 2, next 3, next 3 to 2 is already visited, 3 to 8 and 3 to 4. The next 3 to 8 already visited here. So that next 3 to 4. Okay, 4. Next from 4 to 7 and 4 to 9. So that 7 is first, and from 7 to 5 is there. So now 5 to 6, next 8 and 9. So this is the depth first search. And coming to the BFS, all the unvisited vertices adjacent to I are visited after visiting the start vertex I and marking it visited. Okay, all the unvisited vertices adjacent to I are visited. Okay, next the unvisited vertex adjacent to these vertices are visited, and so on. So that first you can see here 1 to 2. So what are the adjacent vertices for this? 1 adjacent vertices 2 and 8. So from these 2 and 8, first you can choose this 2, and from these 2, what are the adjacent elements? That means 2, 3 and 8. Already 8 is visited, so that now this here 8 is there. Then next 3. So from these 3, what are the adjacent elements? That those are 2, 8, 4. Already 2 and 8 are visited, so that 4. Okay, so that, sorry, before that 8 is also there. From this 8, adjacent is what? 7. Okay, 7. So see first 1. So from 1, what are the adjacent elements? 2 and 8. So first you can choose the 2. So from these 2, adjacents are 3. Okay, 3, and after that 8 is there. From these adjacent elements are 3, 3 already visited. Now 1 is also already visited, 2 is also already visited. So that's 7 unvisited. Now 7 is visited. So then next here, after this 3, adjacent is 4. So that for 4, adjacent vertices are 7, 3, 9. So then 3 for this 4. After visiting this 4, now goes to this 7. So 7 is adjacent to 5. Okay, then next 9 and next 6. That means from 1, 2 and 8. So for this, these 2 and 8 are stored into Q. So which one is first deleted? 2. This is first deleted 2 and 8. After that 8. So then next from 2 to which are adjacent, those are stored here. 3. Okay, from 3 and from 2, 3, from 8, 7. So that 1, 2, 8, 3, 7. So then next and first 3 is removed. For this adjacents are 4. Okay, 4. That means 1, 2, 8, 3, 7, 4. So for these 4 adjacents are 9. So before that 7 is there. So 7 is first removed. So that 7 is first processed. What are the adjacent elements? That is a 5. First 5 is here. Then next 4. After that from 5 to 6. Means 1, 2, 8, 3, 7, 4, 4, 5, 9, 6. So this is about the first such. So next concept is spanning tree. So a tree is connected graph with no cycles. With no cycles is called as a spanning tree. That means a tree is a connected graph. There is no cycles. So from the graph you can find out some tree. So that is called as spanning tree. A spanning tree is a subgraph of G that has all the vertices of G and is a tree. That means then you can ask one doubt, that is what is the difference between the subgraph and the spanning tree. That means in the spanning tree, that is a subgraph of G that has all vertices of G and it is a tree. That means there is no cycles. Whereas coming to the subgraph, so that subgraph contains a subset of vertices. Subset of vertices of the graph G. But here in this subgraph, this is also, we can, spanning tree is also subgraph. But coming to the vertices, this subgraph contains all the vertices, but coming to the edges, it contains less than or equal to the graph. That means here total number of vertices are there. Coming to the edges, total edges are not there in the subgraph, but total vertices are there. Okay, for example, suppose here A to B edges exist, A to C edges exist, from B to C edges exist. Okay, then spanning, suppose A to B edge is there and A to C edge is there. There is no edge in B to C in another graph. That means graph 2. Now the graph 2 is the subgraph of that graph 1. In that case, that graph 2 is called as subgraph as well as spanning tree, because here in the graph 1 contains the 3 vertices, whereas in graph 2 also it contains the 3 vertices, and coming to the number of edges, in graph 1 it contains the number of edges are 3, whereas in graph 2 number of edges are 2. That's why we can call it as a subgraph to that particular graph, but that is a spanning tree because there is no cycles in that graph, because there is no cycles. That's why there is a acyclic graph. That's why that is called as a tree. And it is also subgraph, means compulsory whatever the vertices are exist in that graph, those edges or those vertices are compulsory exist in the subgraph. Then only we can call it as a spanning tree. And coming to the minimum spanning tree is nothing but this is a weighted graph. That means each and every edge is assigned with some weight, that nothing but some cost or distance in some. That means for example here A to B, how much of distance is there? So that distance, okay, that is nothing but cost. That cost is given to the edge. Minimum spanning tree is nothing but this is a weighted graph of G. So this is a spanning tree of G whose edges sum to minimum weight. Suppose you can find out any spanning tree from the given graph. In that case, you can add all the weights of the edges. Those give some minimum value. Then we can call it as a minimum spanning tree. How we can find out the minimum spanning tree? Suppose for example here these are the examples for the spanning tree. Suppose here this is one graph. So here edges exist from 1 to 2, 1 to 3, 1 to 4. And coming to 2, 2 to 1, 2 to 4, 2 to 5. Next from 5, 5 to 2, 5 to 4. From 4, 1, 2, 4, 3, 4. Okay. So this is what the graph. Now you can find draw some spanning tree. So here all in the spanning tree all edges are all vertices are there and edges are not there. So while you are pick the edges, you can follow one thing. In that case, there is no cycle is formed. Suppose you can take 1 to 2 and 1 to 3, there is no cycle, and 1 to 3 to 4. Suppose you can take here 3 to 4, there is no cycle. And for example, you can take here 4 to 2, some cycle is exist because 1 to 3, 3 to 4, and 4 to 2, 2 to 1, some cycle is exist. So you can observe this one. Suppose by forming the spanning trees from a so there is no cycles exist. So that's why in that case that is called as a spanning tree. Suppose you can observe here from 1 to 2 some path is there, 1 to 3 path is there. Suppose and 1 to 4. So first you can take this one from 1. What are the different nodes are adjacent? Which nodes are adjacent to this one? You can take those nodes. Here from 1, 2 is some adjacent node and 4 is some adjacent node and 3 is some adjacent node. That means from 1 to 2 edges there, from 1 to 4 edges there, from 1 to 3 edges exist. So then next you can write all the edges, all the weights here from 1 to 3 to 1 to 6 and here 4. Okay. Next you can take 2. Suppose you can take the edge from 2 to 4, there is a cycle. That means 1 to 2 and 2 to 4, 4 to 1. Cycle is exist. That's why you can omit this 2 to 4. So you can edge this, omit this edge. And coming to 2 to 5, suppose you can take the edge from 2 to 5, there is no problem because there is no cycle is exist. That's why you can take 2 to 5. And after that you can observe from 2 to edges are over. Coming to the 3, suppose you can take the edges here from 3 to 4, here cycle is formed. That's why you can leave this edge. And coming to the 3 to 5, one more edge is there. Suppose you can take the edges from 3 to 5, here cycle is exist. That means 1 to 3, 3 to 5, 5 to 2, 2 to 1. So cycle is exist. So that's why leave this edge also. And coming to the 4, suppose you can take the edge from 4 to 3, again cycle is exist. That's why you can leave. And 4 to 2, so here also cycle is exist. So from 4 to 5 already some cycle is exist. So that's why only 4 edges are there. That means 4 edges, 1, 2, 3, 4. Now it is called as a spanning tree. So in that from this figure you can observe one thing. So if the spanning tree contains, if the graph contains 5 vertices, in the spanning tree how many number of vertices are there? How many number of edges are there? Hello? In spanning tree or in this graph, if the graph contains n number of vertices, then spanning tree contains how many number of edges? Spanning tree contains how many number of edges? Here one is one of the property, that is the tree property is, if
n minus 1, ma'am.
there in the tree, tell me.
N minus 1 vertices, ma'am.
N minus 1
1 edges.
Edges. Why? Because one of the property for the full binary tree, that is if the n number of nodes are there in the tree, how many number of edges are there? N minus 1 edges. That's why here we are saying that spanning tree is a tree only. That's why here if the graph contains 5 vertices, you can observe here how many number of edges? N minus 1 edges. That means 4 edges are there. So now coming to this is also spanning tree. Suppose here 1 to 3 and 3 to 4, 4 to 5 and 1 to 2. So remaining any edge you can take here, edge cycle is formed. So then we are not saying that this is not a spanning tree. When in that case we are saying this is not a spanning tree. Okay. So that's why compulsory మనకి n minus 1 edges మాత్రమే ఉంటాయి. So both of these two are the spanning trees. Okay, but What is the minimum cost? That means suppose you can add all the weights. That means 2 plus 4, 6, 6 plus 6, 12, 12 plus 8, 20. So the cost of this minimum spanning tree is what? 20. Whereas coming to this cost of this minimum spanning tree is what here? 2 plus 4, 6 plus 5, 11 plus 3,
14.
14. Then total cost for this one is 14. So here the total cost is 20. So that's why this is the minimum spanning tree. Okay. Now how we can find out the minimum spanning tree? For this, here two algorithms are there. One is the Prim's algorithm and other one is the Kruskals algorithm. So before discussing these Prim's and Kruskals algorithms, first we can discuss about connected components. To form the spanning tree, first of all, we are known about the connected components. What is the connected component? That means an undirected graph is connected if at least one path between every pair of vertices. That means here, suppose you can observe here, every pair of vertices from V1 to V2, some path is, some edges exist or some paths exist. So from V1 to V3, some paths exist. Okay, suppose you can observe here V1 to V4, some paths exist. V1 to V3 and V3 to V4. Otherwise V1 to V2, V2, V4. So coming to the and you can take any, that means from V2 to V3 some paths exist. V2 to V3 or V4, V2, V4, V3 or V2, V1, V3. Like that minimum one path is exist between any two pair of vertices, then the graph is connected graph or connected component. That means an undirected graph is connected if there is at least one path between every pair of vertices in the graph. Then we can say that the graph is connected graph. So a two pairs mani connect lekapayina kuda we are saying that that graph is unconnected or that is not a connected graph. Okay. A connected component of a graph is maximal connected subgraph. That is, every vertex in a connected component is reachable from the vertices in the component. That means a connected component of a graph is maximal connected subgraph. When we say that there is a maximal connected subgraph, means every vertex in a connected component is reachable from the vertices in the component. అంటే ఏదో ఒక వర్టెక్స్ నుండి ఖచ్చితంగా రిమైనింగ్ ఆల్ ద వర్టిసెస్ మనకి పాత్ కనుక ఎగ్జిస్ట్ అయింది అనుకోండి, దెన్ దట్ ఈస్ కాల్డ్ ఎస్ ఏ కనెక్టెడ్ component subgraph. For example, here this is the subgraph. Here this is one component and this is the this is one connected component subgraph. This is one connected component subgraph. Okay. Here this is the one connected component. Here this figure shows the connected with two connected components. That means ఇది ఒక కనెక్టెడ్ కాంపోనెంట్ అవుతుంది, ఇది ఒక కనెక్టెడ్ కాంపోనెంట్ అవుతుంది. అదర్వైజ్ సపోజ్ ఇది తీసుకొని ఇది వదిలేసాం అనుకోండి, దిస్ ఈస్ వాట్ ద టూ కనెక్టెడ్ కాంపోనెంట్. So here for finding the minimum spanning trees, here two algorithms are there. One is a Prim's algorithm and other one is a Kruskals algorithm. Now see here Prim's algorithm. This Prim's algorithm starts from one vertex and grows the rest of the tree by adding one vertex at a time by adding the associated edges. Okay, Prim's algorithm starts from one vertex and growing the rest of the tree. Means starts from one vertex and until tree form అయ్యేంత వరకు. That means there is no cycles and complete all the vertices. Prim's algorithm starts from one vertex and grows the rest of the tree by adding one vertex at a time by adding the associated edges. While adding these associated edges, in that case you can observe there is no cycles are formed and at the same time minimum cost. That means this algorithm builds a tree by iteratively, that means recursively adding the edges until a minimal spanning tree is obtained. Until a minimum spanning tree is obtained. So that is when all nodes are added. Okay. So at each iteration it adds to the current tree a vertex through a minimum weighted edge that does not complete a cycle. So every iteration while adding a node to the current tree, so in that case you can observe that edge is added to that current tree with minimum edge while adding that one, you can observe one more thing, that is not a cycle. That is not form a cycle. Suppose this is a example. So this is a minimum spanning tree. How this is find out? Here initially there is no edges and there is no pair. So first you can take the set contains only one vertex, that is initial. You can observe the initial vertex is 1. So from this one, here two pairs are there. Okay, that means adjacent edges are 2 and 4. 2 is one adjacent edge and 4 is one adjacent edge. So in that, how we are saying that 2 and 4 are the adjacent vertices? Because here edges exist. So while existing this edge, here some weight is there. So from these two edges, you can pick only one edge, whichever is minimum. Okay, here 1 to 2, 11, cost is 11. From 1 to 4, cost is 40. So that you can take only 1 to 2. Okay, and after that, from the 2, that means now the set contains 1 and 2. From the 2, how many, you can observe how many number of adjacent vertices are there. So now this is 1 to 2 is the tree. Now this is 1 to 2 is the tree. This is now current tree. For this current tree, you can add one edge. So in that case, first you can observe what are the different adjacent vertices are there. Okay, from 2, here 2 to 3 is there, 2 to 5 is there, 2 to 4 is there. That means what is the cost between 2 to 3? 20, 2 to 5, 40, 2 to 4, 61. So from these 3, you can choose which one is the minimum, that is 20. So that you can add 3, that means 2 to 3, connected this, add this weighted edge to this current tree. This is the current tree. Add this weighted edge, which is the minimum, to this current tree. After that, you can take the edge 3. So now here children, edge 1 to 2. That means our graph contains, our spanning tree contains 1 to 2 and 2 to 3. So from 3, first you can observe here from 3, 3 to 6 and 3 to 5, 3 to 2. So already this 3 to 2 already visited. Okay, now 3 to 8. So this is a 80 and this is the 40. Okay, now you can observe these two. Suppose here, suppose here 2 to 5. Okay, from 2 to 5, one more edge is there. This is a 40. So cycle for us. We are not choose this one. Only 2 to 3 is chosen. After this set, you can observe here from 3, 80 is there, 40 is there, and here 40 is there, 1 to 4. So there is a chance for this 1 to 4 and 3 to 6 and 3 to 5. Here 80 is there, here 50 is there, here 40 is there. So that choose now the current tree is 1 to 2, 2 to 3. For this current tree, we can add one edge, weighted edge, that is 1 to 4 with cost 40. Now the set contains 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now 1, 2, 3, 4. So from 3 it is over. And from 4 you can observe now. From 4, so now the edge is 1 to 4. So from 4, what are the edges? That means 4 to 2, 4 to 5 and 4 to 7. So if we can take this is the minimum one. 33 is the minimum. Okay, first you can choose that 33 and add this 4 to 5 edge to this current tree. Now in the set 5 is there. So what is the cost? That is 33. Okay, and after that from 5, here 5 to 3, 5 to 6, 5 to 7, like this. Suppose you can observe here these 50, 81, 72, all these three are maximum to this 40. Suppose you can take this one, there is no problem, that means there is no cycle is formed. So that 4 to 7, you can choose now 4 to 7, this is added to this weighted graph. And after that from 7 to this and 7 to this 6. So from this 33 is a minimum. So while you are adding this one, there is no cycle. So you can choose from 6. And now all the set of vertices are contains in this set A. Okay, 1, 2, 3, 4, 5, 6, 7. So that all the vertices are there. Now how many number of edges are there? 1, 2, 3, 4, 5, 6. So that Prim's algorithm is completed. Now this is the minimum spanning tree. So this is what the minimum spanning tree. For form the minimum spanning tree, first start one vertex and take the adjacent vertices. In that case, add the adjacent vertex to this one with the minimum spanning. So until all the vertices are completed, the next you can observe that how many number of edges are there. So while choose that weighted edge, so that weighted edge is minimum, as well as if you add that weighted edge to this current tree, there is no cycle is formed. So that Prim's algorithm is completed. In that case, this is the minimum spanning tree. For this Prim's algorithm, to add all these edges of this graph, it gives the cost of this graph. That means from, for example, 1 to 2, how much? So this is the minimum spanning tree. Now one more is a Kruskal algorithm. This is a Kruskal algorithm. So another way to construct the minimum spanning tree for a graph G is to start with a graph, that is V dash E dash, new graph. So initial ga manaki edge undadu, that consists of the n vertices of G and having no edges initially. So in the Prim's algorithm, we start with one connected component, add a vertex to one connected component and no cycles. And in the Prim's algorithm, em chestunna manaki every time connected components తీసుకున్నాము, ఆ connected components. So this is one connected component, this is one connected component. Suppose you can add this to connected component, there is no cycle is formed. While choosing that connected component, that contains a minimum cost. So this is in Prim's algorithm. Whereas in Kruskal's algorithm, so first with n connected components. So at each step the number of connected components that would be reduced by 1. That means first you can choose here n number of connected components. Means 1 is one connected component, 2 is another connected component. Like that, initially you can take number of connected components, and in the next step you can reduce it to that connected component into one level. So until ఎప్పటి వరకు రెడ్యూస్ చేస్తాము, వన్ కనెక్టెడ్ కాంపోనెంట్ వరకు రెడ్యూస్ చేస్తాం. అంటే ఇనీషియల్గా this is one connected component, this is one connected component, this is one, like that number of connected components are there. From those, so first you can choose here 1 to 2. Here this is the minimum. And from 1 to 2, 2 to 3, like that. From this graph, 1 to 2, 2 to 3, 3 to 4, 2 to 5, 5 to 3, 5 6, 5 7, 7 6, 7 4, 4 1, like that. All weighted we can take first, and after that choose which one is minimum. Okay, so from this first you can choose 1 to 2. So 11, that means you can write the ascending order. That means 11, 20, 33, 33, 40, 40, 40, 50, next 61, next 72, 80, 81. So these all are the edges. First you can take in ascending order. So in the ascending order, first 1 to 2. Okay, 11. So that is first connected component. Okay, so this connected component, first 1 to 2. Then from this, in the ascending order, 20 is the minimum cost. Now 2 to 3, the next connected component. That means already 1 to 2 is there. So for this 2 to 3 is added. So that now the connected component is 1 to 2, 2 to 3. Observe here, 1 to 2, 2 to 3. That means 2, 3. So next which is minimum, that is the 33 is the minimum. That means 33, 4, 5 and 7, 6. Both are the 33. So that first you can choose the 4, 5. First you can choose 4, 5 first. Okay. Now the 4, 5 is the connected components. So observe here, 4, 5 is the connected component. First added the edge 4, 5. Now the 1, 2, 3 is one connected component. 4, 5 is another connected component. Now take 7, 6. So next one is, that is 6, 7 is the connected component. 6, 7 is added. That means 1 to 2 is added, 2 to 3. So this is a connected component. 4 to 7 connected component. 7 to 6 connected component. So that next, sorry, one more we are left one. That is a 4 to 5. 4 to 5. Okay. 1 to 2, 2 to 3 is one connected component. 4 to 5 is one connected component. Next one is 7 to 6 is one connected component. Okay. After that, suppose here 1 to 3, 4 to 5 is a connected component, 6 to 7 is a connected component. Then next from this, here you can observe here 2 to, suppose you can observe here 2 to 5. So this is also 4 and this is also 4. So already in our connected component 1 to 2, 2 to 3 is there and 4 to 5 is there, as well as 1 to 4 is also there. Okay. Now see here 1 to 2 is there, 1 to 2 is there, 1 to 4, 2 to 3 is there, and 4 to 5 is there, 1 to 4 is there. Okay. And 4 to 7 is there. And coming to this 2, suppose you can add this 2 to 5. So this is the minimum one. Why? Because next minimum one is a 40. 11, 20, 33, 33, 40, 40 is completed. Again 40 is there. Again 40 is there. Suppose you can choose this 2 to 5. Here cycle is formed. Here cycle is formed. That's why you can leave this one. That is, this edge is rejected. Okay. Next one is, so now this is the connected. That means 11, 20, 33, 33 completed. After that 40, 40. Now you can choose this one. Automatically this is rejected. Now this is in the previous case. This is what? Separate one. 7, 6. 6, 7 is separate. 1, 2, 3, 4, 5 is a connected component. Now this is a connected component. This is a separate one. In this case, 1 to this 7, 6 can connected to this component. So that now the single connected component 1, 2, 3, 4, 5, 6, 7 is a single connected component. So now this is what the Kruskal algorithm. That means whatever the spanning tree, minimum spanning tree we get by Prim's algorithm as well as the Kruskal's algorithm, both are same. Okay, but the difference is here in the Prim's algorithm we can choose the initial and after that we can move to other one. While using that one, that adjacent one is the minimum and there is no cycle. Whereas in the Kruskal's algorithm, first we can take n number of components and divide those n number of components, n number of vertices into n number of connected components, and after that you can reduce it to single component. In that case, add one component to other component, choose the minimum cost, and there is no cycle. So that is what the Kruskal's algorithm. So the shortest path between two given vertices is the path having minimum length. So that means shortest path in the sense, suppose you can choose any two vertices, but madhyalo manaki em undali, shortest weight. Okay. Now come here in the applications of graph. In computer science, graphs are used to represent the flow of computation. Okay, how the computations are there. So these Google Maps. So whatever the Google Maps you are used to find one source, some path from source to destination, there we are using this graph. At the same time, we are using this Kruskal's algorithm and Prim's algorithm to find the shortest path. And coming to the Facebook. So users are considered to be the vertices, and if they are any friends, then there exists some edge running on between those two friends. So this is what the undirected graph. So other applications are World Wide Web. That means the pages, web pages are considered to be the vertices. There is an edge from page U to other page. Suppose you can start anything from the Google search. So in that case, that whatever the request you are given in the Google search, so that request based content is connected. So that is another page that contains another page that is displayed. So that one web page to another web page is connected. Here all the web pages are vertices. So this is an example of directed graph. So in the operating system also this graph can use it. Here resource allocation. That means suppose one process is used some CPU. So in that case other process is not used. So in suppose one process is goes to the waiting position. So like that here in the resource allocation graph, where each process and resource are considered to be vertices. Edges are drawn. That means one process assigned with some resource, that resource is not used by another process. So in that case, you can find out there is any complications are occurred. That means how those are executed. So this already we have discussed in the operating system. That means to find any deadlock is there. Deadlock in the sense one process is waiting for the resource and another process is hold that resource. So until and unless release the resource from the process, another process is never used. So that type of situation is called as deadlock. Okay. So in this case, that means these are the different types of applications in the computer science. A different application, that is the Google Maps, Facebook, World Wide Web operating system. Likewise, in the network flow, that means many applications are there in the real life by using these graphs. So here see even examples that the number of elements in adjacency matrix of a graph having 7 vertices. So if the graph contains 7 vertices, how many number of elements in the adjacency matrix? That is 49.
49.
7 into 7. Okay. What would be the number of zeros in the adjacency matrix of the given graph? So first you should draw the graph. Okay, అప్పుడు మనకి ఏమవుతుంది, how many number of zeros, that means here direct గా కూడా find out చేయొచ్చు. Here 1 2 3 4, that means 16 elements.
Right, ma'am.
Okay, how many number of zeros are there? Total number of elements 16. Out of these 16 elements, so here how many
10,
number
ma'am.
of edges are there? 1 2 3, so that 1 2 3 3 2 1, so that 6. Okay, from 16 minus 6, total 10, isn't it? 10 zeros are there. Kavalante you should draw the find out the adjacency matrix for this and count how many number of zeros present in that graph. That means 10 zeros. So direct shortcut enti ante here how many number of elements? 4 elements. Okay, there is no self loops. Okay, 4 elements are there, that is 4 vertices are there, 16 elements are present in the adjacency matrix. Here there is no self loops and 3 edges are there, 3 into 6, that means here 1 2 3 3 2 1. So like that twice, means total 6 ones are there, and out of these 16 elements are there. Out of 16, 6 are the ones and remaining 10 are zeros. So that answer is 10. అంటే మీకు డ్రా చేయకుండా డైరెక్ట్గా చెప్పేయచ్చు. సో ఏ గ్రాఫ్ విత్ ఆల్ వర్టిసెస్ హ్యావ్ ఈక్వల్ డిగ్రీ ఈజ్ నోన్ యాజ్
Regular graph.
degree is known as what? Equal degree nothing but every vertex contains the edge with remaining all the vertices. Then we can call it as a regular graph. This is called as a regular graph. So this is about graphs concept. So only we are discussed here the concepts, and remaining concepts also there. There is a Euler's graph, Hamiltonian graph, next Walsher's algorithm. Next we can discuss about different types of graphs also. So tomorrow we will discuss about those concepts. After completion of all the concepts only, we can discuss the questions regarding these trees and graphs.